That's working. Okay, great. So we're going to take the opportunity of this talk to sort of share with the group the things that we're working on here at UNR. And it's sort of a survey of recent work on attention and working memory and some preliminary data, the behavioral data that we've been collecting that we're pretty excited about and think may be of interest to the group. So this spans perception, attention, and working memory. And I'm going to take advantage of the expertise of the group to sort of gloss over a lot of the sort of background and nuances. So I encourage you guys to interrupt as needed. So first, I'd just like to thank you guys for launching the website. I don't know who these beautiful children are or where this place is, but the goal of our talk is to sort of get to know us out here at UNR and to give you a sense of. Are you seeing our faces? Everybody's face. Oh, I don't know how to.
Yeah, on the side.
Yeah. Ooh, that's good. Okay. What have I done? Okay, so the topics we're going to cover, I'm going to talk about a novel technique for probing neural correlates of visual working memory encoding using EEG. And this is something that Marian and I have developed over the last several years and have applied to various levels of success. And then Marian is going to discuss the allocation of attention to items in visual working memory. And this is going to be quite different from Peter's approach to the sort of the verbs of the contents of working memory, and maybe a little bit more direct to what we think about attention. And this are findings from the quote unquote retro cue paradigm. And then I'm going to share, we are going to share preliminary data from behavioral studies examining oscillatory mechanisms underlying spatial attention, internal attention, and perceptual organization. So that's what the talk is about. And then we're going to, if time allows, just have a little slide. We are very interested in leveraging our consortium to collaborate and just want to sort of plant some seeds of areas in which maybe we can team up with you guys and help. Okay, so visual working memory, we all know about it. It's capacity limited. And when we run experiments in which we ask people to hold on to more and more items, our ability to do so asymptotes out. The literature will claim at about 4 items. Our students here at UNR, I don't know if it's brain damage or something, tend to be around 2.5. I'm more close to like 1/2 an item. But anyway, there's a big push in the literature to identify neural correlates of these capacity limitations. Where are these capacity limitations coming from, why, and at what stage of working memory? And probably the most commonly cited study of this is an MR study by Todd and Marwa. It's now over a decade old, showing that in regions of posterior parietal cortex and the intraparietal sulcus, the bold response will asymptote both with a number of items that you're attempting to, or will correlate with the number of items that you're attempting to hold on in working memory, and asymptote to a measure of overall capacity, and here where it's between, 3 and 4 items you're asymptoting. But one of the challenges in identifying, where these capacity limitations are arising and what function they're serving has been something that's bugged me for years. And it really falls out of the paradigms used to test working memory. And working memory is typically divided into 3 phases: encoding, maintenance, and retrieval, where during encoding, you're presented with an array of items, they disappear, and then depending on the nature of the task, some sort of a probe screen during retrieval is shown on the screen, and you're asked to report, what it is that you remember at encoding. And so in a classic recognition paradigm, what I'm showing here, you might be asked to say, is this an old item or a new item? In this trial, it would be an old item. The star had been presented at this location. But the challenge that working memory plays in identifying the sources of the capacity limitation is the fact that we have temporal collinearity of the stages of working memory. That maintenance must necessarily follow encoding and retrieval must necessarily follow maintenance. And while we can systematically vary the duration of the maintenance period to create sort of jitter and separability between retrieval, maintenance, retrieval, and encoding, we don't have the ability to temporally separate encoding from maintenance. And so in an attempt to identify neural correlates of capacity limitations and identify whether these capacity limitations are arising due to a maintenance process or an encoding process, people have really gone through great, I would call, logical exercises to separate maintenance from encoding. And so in MR studies, there will be a selection of TR that gets operationally defined to correspond to the retrieval period or the maintenance period or the encoding period. But these are really operational definitions, and there's very little reason to believe that a bold response at 10 seconds, which is being operationally defined to be a maintenance process, is in fact selective to something that's occurred after the stimuli have been removed from the screen. And the temporal resolution of the bold signal, this is a really big problem. And while it might be fair to say, okay, the bold response to a flashed array is over by 16 seconds, that's reasonable. But really separating the maintenance from encoding is quite challenging. Now, there's a fairly large body of literature in EEG that has much better temporal resolution, and there's a very common waveform, EEG signature, that is used as a neural correlate of working memory and has been shown to exhibit the characteristics of a capacity limitation, and this is the contralateral delay activity. And so a stimulus is shown at time 0, it lasts 100, 200 milliseconds, disappears from the screen, and then on electrodes located over really parietal cortex, you see this sustained activity that increases in amplitude as a function of the number of items that are being held in working memory and has been shown in many studies to plateau, much like the bold signal from Todd and Marois with the capacity limitation. And because of the temporal resolution of the EEG, it's perhaps more of a reasonable assumption to say, okay, the stimuli are off the screen here. They've been off the screen for several hundred milliseconds. Therefore, the signal we are seeing really represents maintenance processing. And while that's somewhat reasonable and has certainly been argued many, many times, I'd just like to point out that the electrophysiological response, the EEG response, evoked potential to visual stimuli, an encoding screen flashed on the screen can last several hundred milliseconds. And before I even went to graduate school, we recorded auditory evoked potentials, very transient in nature, on the order of single millisecond tone pips, 1 to 10 millisecond tone bursts. And you can see evoked potentials that last well over a second. And so this notion that just because you're here at 500, 600 milliseconds after the stimulus has been removed from the screen, that represents a purely cognitive response and is not a perceptual response is an assumption. And so this has always bugged me. And the question is, how can we separate encoding from maintenance? And the technique that Marian and I developed was to use frequency tagging to isolate the encoding period. Can we find an EEG signal that is temporally isolated to when the stimuli are on the screen?
Gideon?
And so to do this, Gideon? Yes.
I'm just curious. I mean, you pointed out, I guess rightfully so, that the operationalization of these terms is something that's concerned you, but are you going to help us distinguish what you have in mind between encoding and maintenance and why during a period in which you're encoding, you're not also maintaining?
Okay, that's a fair question. And I think the literature, that's a very good question. And so we have an operational definition, which is if the stimuli are on the screen, you're not purely maintaining. Now, and we lump everything that's going on while the stimuli are on the screen as related to encoding. And that could be, there's reinforcement, you've begun a maintenance process and you're able to reinforce it. But once those stimuli have disappeared and there's nothing left to look at, you're in the maintenance, now you're in memory zone. So we are, once again, operationally defining what encoding means. But yes, there can be maintenance occurring while the stimuli are visible. So the technique we use this is to present items in a visual working memory display that are flickering. Each item flickers at its own rate. And we do this for 1 second, which I think is a long encoding period. But it's while the stimuli are on the screen, each stimulus is flickering at its own rate. And so what we can do, yes.
Isn't it a problem if the 12 hertz one is a harmonic of the 3 hertz one? Do they have to be different?
Yes. So, right. So I'll show this here. They are separable. The frequencies that we choose, and this is a challenge of identifying these frequencies. And it's not an accident that we've chosen the frequencies that we have chosen. So these 4 frequencies, 3 hertz, 5 hertz, 12 hertz, and 20 hertz, are linearly separable up to the 4th harmonic. So 12 hertz is the 4th harmonic of 3 hertz, 20 hertz is the 4th harmonic of 5 hertz. There is, unless you've got an incredibly strong signal, which you can get either by very long presentation periods or many trials, the 4th harmonic is virtually indetectable in the EEG. And so there's very little contamination in the 20 hertz response from the 5 hertz response. But you, for example, wouldn't want to have a 3 hertz flickering guy and a 6 hertz flickering guy. Now, what we can do is extract the data, the EEG epoch for each trial for that 1 second encoding period, and perform a Fourier transform on it, or the average of those epochs across the experiment, and isolate individual frequencies corresponding to each item. So we can look at the 3 hertz fundamental that would correspond to the response to the 3 hertz stimulus, or the stimulus that's flickering at 3 hertz. Similarly, the 5 hertz, 12 hertz, and 20 hertz responses, and their second harmonics. We've looked at for the 3rd harmonic, and it's not really detectable, and the 4th harmonic is certainly, in the absence, not detectable. And so we can design an experiment in which we show the items during encoding. They flicker. A probe item occurs after a delay. A probe item occurs, and the subject asks, is it old or new? And we can then sort, for a given trial, each frequency as a function of whether it was a probed item or an unprobed item, 1st or 2nd harmonic, and was it correctly remembered or not.
It's shown flickering, Gideon, in the probe?
In the probe, it is not.
Okay.
And I'm not sure it would matter.
Well, it's only if you encoded the rate at which it flickered that could confuse you if it was incongruent or something.
Yes, that's actually something we haven't thought about. My hunch, I mean, these are, well, I don't know. That could be done. Are you encoding the frequency? In fact, there's a question of if that frequency became task relevant, is there a chance it could be maintained during?
The full report data suggests you're not.
Okay. So Marian, we're going to show some other data that Marian suggests we're not paying attention to the frequency, but we could make it task relevant. And we've always had this sort of fantasy, could you see these frequency tags persist through the maintenance period? But we don't know yet. So basically what we find is that if you look at the amplitude of the responses to the probed items that were correctly remembered, they are greater in amplitude than they are for incorrect items. So we're seeing during encoding a neural correlate of whether or not you correctly retrieve or remember the item. The correct tags are greater than the incorrect tags for the probed item. Now, although we can't know whether or not they got the items correct or not, we can look at the unprobed items on correct and incorrect trials. And you say, you got the probed item correct, what's the response to the items we didn't actually probe? And we also see that on correct trials, you have a greater response, suggesting that at least on some incorrect trials, there's sort of a complete failure to maybe encode or retrieve anything. And we see this this was done on a low density EEG system, and it didn't really matter what electrode we were on, whether on the sort of centrally located electrodes, you see a very similar pattern, or on occipital electrodes, you also see the same pattern. And so we're able to see a neural correlate of working memory accuracy, which I take as a measure of capacity limitation during encoding.
Did you not see contralateral bias for the response? Because the items are actually in each visual hemifield, right?
Yeah, we weren't able to sort the data with that precision, just as a number of trials issue. And so that's something that is conceivable for future work. So this is collapsed across all trials. And so it's not entirely clear, for example, is this effect being driven by correct and incorrect items when the probe was on the right visual field? And this would be on the left visual field. We don't have that resolution yet. Okay, so then we want to follow up on this probed, unprobed item sort of question where we say, well, look, let's just go to a full report paradigm. And now within a given trial, we can see what are the frequency tags in response to the correctly remembered items and incorrectly remembered items. And so here, what we're going to do is we're going to show 4 items. They're each flickering, you maintain, and then we actually have 2 retrieval paradigms, one where you select the box, and then you select the item that you remember being in it, and then you can do this self-paced in any order that you want. And we call that the simultaneous probe. And then we have a sequential probe in which we dictate the order in which you must respond. So we put a green box, we say you must respond here, and the person clicks, which is the one that was in this corner, and then we, in a random order, walk you through the response screens. And in general, the sequential probe is more challenging in that, if I have maybe I have some sort of strong representation of this 4th guy, I've got to kind of hold on to it through the other response screens in a way I don't have to in the simultaneous probe. Now, we did this with our high-density EEG system, and again, what we see when we can now isolate the response to the correct and incorrect items within a trial, that again, and this is sort of replicating our initial finding, the correctly recalled items produce a larger frequency tag than the incorrect items. And this is within an individual trial. And we're really working on ways of evaluating significance when we have 256 electrodes. And basically what we're doing here is just sort of rank ordering them by significance, where the red line is a P of 0.05. And both of these, correct me if I'm wrong, you guys, but these are like an FDR correction that's also like these are not false positives. Not many of them are false positives. Um, so in addition to looking at the frequency-specific, the stimulus-specific responses, we can look at what's known as induced power, where we throw out phase information, and look not at individual item responses, but more task-specific items. While the person is encoding the trial, what changes do we see in the power spectrum of the raw, in essence, in the raw EEG in a non-phase locked manner? So this has nothing to do with the flickering of the stimuli. And we can break this down into the classic frequency bands of the EEG. And so for the very low frequency delta band, which is 1 to 4 hertz, sorry, I should have like a little black bar covering this up, but 1 to 4 hertz, we see there's really no significant increase or decrease in the power of the delta band as a function of the number of correct items that you got. So we compare, you got 3 or 4 items right compared to you got 1 or 2 items correct on a trial. When we look at the other frequency bands, we see in the theta band 5 to 8 hertz, and we're sort of defining what the cutoffs for these frequencies are based off of various papers. There's some debate as to where the boundaries really should be. The alpha band, 9 to 12 hertz, and even slightly higher in the beta band, we see an increased power primarily during the harder task, during the sequential probe task. You see increased power in theta, alpha, and beta with the more items that you got right. And we don't really see that same pattern of increased power during the simultaneous probe. And so there are 2 real takeaway messages here. One, that we see this during encoding, whether you get something right or wrong, and the number of items that you get right or wrong. And this is, what people like to call capacity limitation, both in a stimulus-specific fashion, but also in a task-specific fashion, and that our retrieval demands, the nature of your retrieval task, can influence these encoding-related processes. The fact that the sequential probe is challenging in a certain way seems to be altering the way people are encoding the stimuli. Now, the last study I want to share with you on in this line of research, the classic demonstration of capacity limitation are what are known as set size effects, that the bold signal goes up as you have more items that you are retrieving or holding on to in working memory. And so we want to know, do we see set size effects during encoding? And so what we have is we have 2 placeholders, which are squares that are never probed. And on a given trial, and subjects are informed, if there are squares, ignore them. They will never be probed. And just try to encode the 2 items if the squares are present, or if there are no squares, try to encode all 4. And so we can have a set size 2 or set size 4 condition. And then again, we can compare responses to correctly retrieved items as a function of whether it was part of a set size 2 or set size 4 trial. And what we find, and this is somewhat interesting, is that unlike what you see in the bold signal or the contralateral delay activity, in which more items means more signal, what we see is for an individual item, more items means less signal. That the response to a correctly recalled item, when it's one of 2 items in the encoding stage, has a bigger frequency tag than for the set size 4. And we see this predominantly on frontal electrodes. And this is at the second harmonic. So when we put this all together, this is sort of summary of this line, we can extend these steady state visually evoked potential techniques, the frequency tagging, to visual working memory, specifically to isolate the encoding phase and avoid this separability of encoding and maintenance. The higher amplitude frequency tags are observed for items that are later remembered. And we get higher amplitude frequency tags to individual items when they are in the smaller set size. And retrieval demands can influence the induced power during encoding. Now, these are sort of the summary of what the actual findings are. And if we put it together, okay, encoding related resources, what I would call, what are they? It's attention. Now, we're not doing an explicit attention task, but for the sake of our grant, I would call them attention. They're capacity limited in that you are not uniformly distributing items across uniformly distributing your encoding related resources across items during the array. And we haven't gotten into the fixed slots flexible resources, but our data are much more consistent with a flexible resources hypothesis versus fixed slots. But what's interesting is most of that literature is really focused on maintenance, and we're seeing this during encoding. So, and I think that's very, very important because it highlights the important role of attention in working memory and working memory capacity. So I'm going to pass it off to Marian now, who's going to talk about shifting attention to items held in working memory.
Hi. Make sure you guys can see me. Just shift the camera down. Oops. What do I do? Okay. So over the last few years, my lab has been spending a lot of time investigating a question about how we shift our attention among items that we're holding online in working memory that are no longer available to perceptual processing the same way items are available when you are looking at them. And the way we've been doing this is to use the retro queue paradigm. And the retro queue effect is essentially flipping a Posner queuing paradigm such that you present the queues well after encoding and maintenance have already transpired. So in this first bullet point here, what you're doing is presenting some kind of visual cue. And what happens is that people's performance accuracy improves and the reaction times tend to go down. And this work was initially this paradigm was discovered over a decade ago. And the reason we think it's helpful is that it lets you manipulate how people are shifting their attention among items already held online, and what are the parallels between perceptual attention, something we sometimes refer to as perceptual attention, versus this more internally directed shifting of attention among these representations held online. And the way it looks is like this, so this should look fairly familiar. You have your fixation, some kind of visual array, a delay that lasts the standard working memory delay duration of about a second, after which point then a cue appears. And so these kinds of cues have been manipulated. This centrally located X is something we use often as a neutral cue. We've played around with these various cue types, and sometimes it matters, sometimes it doesn't, and often an arrow indicates the item that is likely to be probed next. So it may be valid, it may be invalid. So a lot of these various component pieces have been played with, but essentially it works like a standard working memory, and then instead of the standard recognition probe appearing, you have a cue and then a second delay, and then some kind of recognition report probe task. So you're way after any influence of something like iconic memory could be participating in improving your performance, and you get no additional information about the items you encoded. So what you've got is simply what you brought with you from that initial encoding experience, and this cue type helps you identify with better performance what item was actually there. And the way we typically present these data is showing the difference in accuracy reaction time between the neutral cue and, say, a valid cue type. So these are some data from our lab, and the results are surprisingly robust. At least they're surprisingly robust to me. They usually are somewhere between 5 and 15%. And the reason they're surprising to me is that working memory capacity is strikingly capacity limited to approximately 4 items and falling. and you don't get additional information. So this is something that helps you. And furthermore, we don't seem to see much of a cost when we lie to you and tell you, when we provide you with an invalid cue, that doesn't reduce performance below a neutral cue. So it seems like a win-win, and it's something we've been interested in following up on. So to provide you with an example of this, one of the lines of inquiry we've been following is to find out whether this way of thinking about attention is really if there are any quantifiable differences between attention operating on items held in working memory compared to what people have been reporting and studying for years and years in the perceptual domain. And in this first stab at this, the way we manipulated that probe was to look for benefits for a successful positive retro cue effect as a function of cue type, whether you were pushing attention around using endogenous or exogenous shifts. So we had a neutral cue, this X. We had an exogenous cue, a dash that would appear and draw your attention to the location that was to be probed later on. We used that centrally located arrow, which we considered sort of a hybrid mix of bottom-up and top-down attentional manipulation. And we used an endogenous cue of a number that was coded to each location in the visual array. And this 400 milliseconds I've circled just to highlight that it is not, that it is well beyond, the cue is not driving this effect. And 400 milliseconds is the timeline we commonly use for this second delay. But I think I'll show you some data on that later. We've played with that number. And what we found was that the cue type did matter. So this marked some data for us showing that this way of thinking about shifts of attention and internal attention was showing some differences from what we know about perceptual attention. And that's because we see this retro cue effect between that hybrid arrow cue and the neutral cue, which is this retro cue benefit, but it didn't extend to these other two cue types, either that exogenous spontaneously appearing flash or that centrally located number cue that required remapping. So we took this as evidence that there were some differences between these different forms of attention. And work out of Yu-Hong Zhang's lab suggests that there are some other differences, that you can't divide these the spotlight of attention among multiple locations. And there's some other findings that suggest that there are some differences between these two forms of attention. And I didn't know how much time I would have since I tend to be a faster talker than someone I know. Yeah.
So I don't understand the difference between the arrow cue and the number cue. Both of them seem like endogenous symbolic cues.
Well, the arrow cue, there's a pool of literature out there suggesting that because the arrow cue is overlearned and so well practiced from a very early age on, that it is not fair to consider it as a purely endogenous cue. But your point is well taken. And so this is why we considered it more of a hybrid, is that it has been so overlearned that it acquires the ability to shift attention on its own from both of these sources, from exogenous and endogenous roles. But you could take issue with that. So we've played with cues some more, and that exogenous pull, that ability to get a retro cue benefit with a purely exogenous cue, is harder to do. And more recently, we've pulled some tricks to make it happen, but it's not as easy as this arrow cue. We've looked at we've conducted a number of studies trying to understand various aspects of what is driving the retro cue effect and what matters. And I've listed several of these here. This sort of tells a story, and I didn't present data figures for each of these because they typically show the same thing, that there's a retro cue benefit, and in our hands it varies from 5 to 10% in these trials. So some of the questions we've been asking that may be of interest as we progress in our collaborations with groups. Does it seem to be under pure cognitive control? partially, but people can ignore those cues if they're not helpful. People tend to be much more confident on their valid trials. It seems to require central resources because when you pair it with an overlapping secondary task, performance falls. The full magnitude of the retro cue effect. Was there a question? I can't tell. No? How fast does the retro cue effect emerge? It appears if you vary that second delay duration, the full magnitude of the retro cue effect appears to emerge around 300 milliseconds and remains constant. So if you have longer delays, it doesn't reduce. We've tested that out to about 24 seconds, which is a way to incur hatred from many undergraduate participants. And we've also done that out to 10 seconds with a full recall paradigm, and performance is better preserved at those longer second delay durations for the valid trials than for neutral trials. Does the position of the central cue, does the nature of the probe cue, do any of those things seem to matter? Not that much, is what some newer data we have is telling us. And what happens on invalid cues? So these are the trials where the cue indicating a particular orientation is misleading. And there doesn't seem to be much of a penalty, but there does in full report paradigms, there does seem to be a greater recall error. I'm sorry, in recall paradigms, there's a greater degree of error, suggesting that in recognition paradigms, you don't see much of a cost, but when you're held to the fire and you have to produce a faithful representation of what you remember, you're not as precise. So this is some of the work we've been doing in using this incredibly robust retro cue effect. And I wanted to plot these data in particular to say the way we've looked at these data has been to select discrete values for say this second delay duration of 100 out to 700 milliseconds. And showing these are data showing that retro cue magnitude emerges around 300 seconds and remains unchanged out to 700. We have purely looked at it in these discrete isolated values that we've supplied. And I think many of us do this. You keep trial numbers properly counterbalanced and evenly represented. But at the later portion of our talk, when we start mentioning oscillations, this becomes important because it has prevented us potentially from seeing some aspects of attentional shifting that are becoming more and more interesting to us. Okay, and I guess that's your segue, Gideon, because you wanted to talk about the oscillation.
Yeah, it was actually a very nice segue. So I want you to keep this figure in mind and note what Marian mentioned, that this retro cue, this sort of significant retro cue, actually extends well beyond 700 milliseconds. And I think he said out to 24 seconds. Okay, so really inspired by Sabina's keynote address at VSS and the work of Rufus van Rooyen, we've been looking at, we've begun a series of investigations into behavioral oscillations, with the idea, the central idea being that attention and perhaps other perceptual processes are mediated by neural mechanisms that are oscillating. And Sabina and Uri Salman have this very nice paper looking at the pulvinar, I believe it's LIP and V4, showing the establishment of 8 Hertz oscillations during attention tasks. And have reported that in doing attention tests, and there are these sort of reports really going back almost 100 years, little hints of evidence that behavior can actually oscillate. And so I want to just give you a flavor for what, when I say oscillate, what that means, and the experiments we've been sort of replicating from other domains to just get our feet wet in this domain. And so here's a standard endogenous task, but maybe it's not as endogenous as we think. This arrow, as we know from David's work, all shapes have sort of a implicit directionality, and arrows have a very strong implicit directionality, I believe. But anyway, we call this an endogenous task, so fixation, the cue shows up, and then subjects are told to report one of the 4 items is going to be tilted either to the left or to the right. 80% of the time, I think it's 80%. 80% of the time, the tilted item occurs at the cued location, and they have to respond, is it tilted to the left or to the right? And what we can do is we can systematically vary the time between the cue and the target. And so in this experiment, we, in essence, randomly choose an ISI between 300 milliseconds and 1100 milliseconds. And within, I think, we're doing this at 85 hertz on an 85 hertz monitor refresh. And so we have very high temporal resolution. Unlike here, where we are at 100 millisecond temporal resolution, we're now in, I believe it's like 12.5 millisecond temporal resolution. And we smooth the data to get a little bit more power, but I just want to show you what the data look like. And I'm going to start, I believe, with an individual subject. And so what we're going to do is we're going to plot normalized accuracy. I'm just going to detrend the data, and we're just going to plot normalized accuracy as a function of the stimulus onset asynchrony, of that cue to target interval from 300 milliseconds out to 1100 milliseconds. And so here's a single subject. We selected this subject for obvious reasons, as you will see. It oscillates. They oscillate. And the oscillations are quite large. It is not flat across time, but it oscillates. And so we're seeing, here at 600 milliseconds, we're 10% below mean performance. We go, 50 milliseconds later, right, we're 30% more accurate. And then 50 milliseconds later, we're back down. And this repeats itself over and over again. We can compute the amplitude spectrum here for this individual subject, and we see a primary oscillation at 10 hertz, and another one here slightly below that. I believe that's somewhere around 8 hertz. We've really struggled with figuring out how best to assess significance of these oscillations, and we've devised a permutation test in which, well, it's not really a permutation, a bootstrap test in which we simulate performance. We sort of do an ideal observer sort of modeling, and we can assess significance at the 0.05 level for each frequency. And for this individual subject, we see that 10 hertz oscillation is significant. Now, we ran many subjects. And so here's the group average. So we just take the single subject, we've got 50 of them, and we average these time domain waveforms together. And that's what we're seeing here. And then we can compute the power spectrum of that. Now, what we see here is, again, the data are not flat, right? That's the real take-home message. The data are not flat. They oscillate. There seems to be 2 primary frequencies present here. A low frequency, which you can see kind of this big hump where performance is better in general from 500 to 700 milliseconds. This is something that we do not detrend out of the data. And when we look, and I don't know how important this really low frequency thing is or not, but when we come to the group, and we can assess significance at the group level, we see there are several frequencies that are reaching significance. Here we are at about 12 hertz. There's another frequency at 8 hertz, and this is that very low, it's really like a 1 hertz oscillation. We've encountered some issues in dealing with these data in terms of the number of trials per bin when we do this and the length of the experiments. And so we really just set out right away to replicate. And so we refined the task where we just have 2 locations. This sort of allows us to increase the number of trials at least for an invalid location, but we're not looking at invalid data yet. And we've shortened our temporal window. So now we're going 300 to 800 milliseconds instead of all the way out to 1100 milliseconds. And we reduced our sampling rate. So our effective refresh on the monitor is 42 hertz instead of 85 hertz. And this just allows us to have many more trials per time bit. And so here's a single subject, and again, we see them oscillate. This isn't the same subject, but here's a big oscillator. And here, what we see is, again, they're showing, well, I wish I could move this, but a peak at 15 hertz, which is the more rapid up-down that you're seeing, and a 10 hertz oscillation. At the group level, we're now up to 13 subjects with the group. Again, the group is oscillating, and it's coming out significant at N of 13 at the 10 hertz, and maybe with more data, this 15 hertz comes out. We tried it with an exogenous cue, flash in the periphery. Again, the subject will oscillate, and here's the amplitude spectrum for that subject, somewhere 15, 16 hertz, 10 hertz. In the group, here's the group average, N of 57. So again, this is averaging in the time domain. So we're preserving phase across subjects, which I find somewhat fascinating. So across 57 subjects, people are, yes? Okay. People are, at 300 milliseconds, people are 10% better than they are at, 40 milliseconds earlier, and 15%, and it just oscillates. I mean, to me, it's kind of incredible, and not what I sort of didn't believe we'd see this. That's just my skepticism with the literature.
Do you think this can account for the attentional blink?
I don't know. We really don't know. I mean, maybe we should be measuring the attentional blink in much finer temporal resolution. Is it the case that, when you look at the attentional blink, it's like time point, time point, time point, time point, time point, and you get, you recreate this. And is the attentional blink, would you see some sort of oscillation? I don't know. But these are pretty pronounced effects. I mean, this is a 15% difference right here. And that's on the order, if not bigger, than what you typically see with the attentional blink. And within individual subjects, these oscillations can be profound. And we have subjects where it's a 40% oscillation, and where they're down at chance, or if not even slightly below chance. And then 50 milliseconds later are up at 80, 90% performance. So
does every subject,
yes,
every subject's contributing to every point, I assume?
Yes.
Okay.
Yeah, every subject's contributing to every point. And I want to make something very, very clear, and then this is in my summary, we're not going to show all 57 subjects. There is an enormous amount of individual subject variability. So here you see in the group here, group average 57, this peak is sitting here at like 8 hertz, 9 hertz. This individual subject is at 10 hertz. They don't have a peak, they're not oscillating it. So, the group is not really reflecting the individual subject.
Well, even on the first one you showed, that was very clear, because the first one was 10 hertz, and that 10 hertz point on the average was essentially nothing on the previous.
It was nothing, exactly. And so this is fascinating. So this raises a question. Well, what makes somebody a 10 hertz oscillator and somebody else an 8 hertz oscillator?
But it also suggests that your approach by doing the group average and the amplitude spectrum on that average is probably not the best thing to do, right?
Yes. And this is something that we are looking forward to working with the consortium of how best to really be looking at all these data. And so we're treating this as a true pilot preliminary data set. These data sets as saying, look, these things are in the literature. Sabina made a pretty big splash with her electrophysiology work and her talk at VSS. We thought we'd go out, see if we could collect the data, sort of replicate what we're seeing with her data. We're not getting the exact same frequencies that she saw. She saw 8 hertz and 4 hertz. She didn't show hints of this 12, 15 hertz thing. Now that may be, and there are questions of why, but I think this is an area where maybe we can all sort of get, some synergy. I don't know. But so those are our investigations with spatial attention, and Marian's going to walk you through, because we've done this with the retro cue.
Thanks for your patience as we swap in and out here. So these next few slides extend what Gideon was speaking about just now, except instead of changing the duration between the cue and the arrival of the stimuli, here we're manipulating, here's our cue appearing, and we're manipulating the second delay duration, so the time after the retro cue has disappeared. And again, we were curious to see and to find out whether there'd be any oscillations at all, any evidence of non-flat data and our lowering the bar kinds of hope. And we were curious to see whether, if there were any detectable patterns, whether they would be consistent with what he was seeing in the attentional spatial attention tasks. And so here's a prelim group of 11 people. And what we've plotted here is performance accuracy for the valid retro cue trials in blue, and the red are the neutral trials. This is just 11 participants, which is, I think, clearly showing a retro cue benefit across the entire range of those second delay durations, although the acute observer will notice they are not flat. And if we detrend those data and overlay them, it is at the group level, we see that these oscillations line up fairly well with each other, we think. We know it's not the most beautiful, but I think it's pretty exciting that we see that any overlap at all in the peaks and valleys here. And in this subset down below, I've presented a single example participant to demonstrate that this doesn't just emerge out of weird group data. If you take the blue and the red lines and subtract them, and this is again open for discussion about what the best way to analyze these. So far what we have done is to look at the magnitude of the retro cue benefit over that second delay duration time window. And again, you have the group of those 11 participants shown in the larger figure, and an individual participant shown here in the inset. You see that again, I won't make a greater claim than to say that these are non-flat. And again, Gideon has implemented the same analysis he described earlier, and of using those simulations to try to identify which of these this is in frequency space, sorry, which of these peaks, if any, are reaching significance. And so in this particular set of group data, when looking at the retro cue effect in frequency space, you see this lower peak that does seem to be somewhere around 2, and then this much broader waveform here. So we'll be collecting data on this pretty intensively. I look up to make eye contact with those who actually will be collecting data intensively over the next few weeks to try to get a better handle on what are very preliminary data at this stage. But we think that these are remaining to be not flat, and that is the claim I am comfortable making at this point. So in the spatial attention cue, there's evidence of some oscillation. In this retro cue paradigm, there's evidence of some sort of non-flat, potentially oscillatory pattern emerging. And Gideon will present a final iteration of these kinds of experiments looking at change in performance accuracy in perception. Thank you.
Actually, Marian, quick question. How do you interpret the neutral cue? Is that like a phase alignment or what? I mean, because it doesn't really offer any, it's just a timing cue.
Right.
That
Right. So we have it in there to control for any abrupt changes of arousal or interruption by the fact that something appears and goes away. It gives you no information. It just says the probe window is coming. So it certainly is there to try to keep everything equal between those two different types of trials.
But you still see the oscillations.
But you still see oscillations. So one possibility is that whatever you're doing, there are these rapid coming and going in and out with phase of attention that's operating at a much faster rate than I certainly previously appreciated. Or maybe it's artifactual. I don't know, but I think we're seeing it in enough participants. We also ran another preliminary study I'm not showing here where we saw the same thing in a larger number of participants. So I'm beginning to think that there's actually something to the reality that no matter where you are or what you're doing, your ability to adequately attend and perform well on a particular task is oscillating. That's all I could,
Hi. Oh, before you go, could you also, I mean, it's not that different, consider the inverse of that the effect of the cue is actually some oscillating inhibition or oscillating disruption, and that it's just taking notches.
Right. Right.
Yeah.
So we see that performance, performance is, right. You see that there is these valid cues are associated with greater performance, and the neutral cue is non-flat as well. When you subtract them, you see that there are largely benefits. And one way of thinking about that is whether we see some penalties is to look at the retro cue detriment or impairment that any individual participant experiences over the full second delay duration window. And there are time points for every participant where the curves cross, where there is a penalty associated with having a directional cue.
I'm just suggesting that the oscillations may not be of attention; they may be continuing ringing interference from the cue itself, and that attention.
Yeah, we're gonna have to, yeah, absolutely, okay. And we're gonna have to play with the temporal variables on this for once we figure out what we think is going on, then we'll have to shift that window much longer for sure. Good point.
I'd say those, given Gideon's point of his older EEG auditory responses, it is something to consider because those kind of keep going.
Yeah, right. So we've been looking out to 1500 milliseconds after the cue, and we would very likely run follow-up studies where we have something like 2 seconds to 3 seconds as the window, something like that. Because in our previous findings, when we use discrete time points, the magnitude of the retro cue effect hasn't shifted that much. But we'll find out.
So I think if I understand your point, Patrick, you say, well, look, if there was no cue at all, whether it's valid or neutral, maybe you're going to perform even better. And what happens is this cue shows up, and even if it's neutral, it sort of interferes with your memory process. You're trying to hold on to these 4 items, and this damn X appears in the middle. And that could sort of
side of, like the dark side of attention. It's negative attention. It's masking, right?
Right. And to follow up with you, David, there's this very nice work by Ian Feeblecorn and John Fox showing that the cues can serve as sort of a phase reset. And so that neutral cue can sort of serve, and they do this where you play a tone or something, it'll reset ongoing oscillations. And so it's not entirely clear, why should a neutral cue oscillate and lead to an oscillation in performance that's in phase with the valid cue, but it may be this phase resetting that Feeblecorn and John Fox have studied.
So Gideon,
yes,
it's 3 o'clock now, so you should try to wrap it up.
Okay, we're going to finish up. This is very easy. Okay, we see it with like Kanitzas where we put a mask on. So here's a single subject. They oscillate where we're varying the time between the stimulus and a global mask, and they oscillate, and it's significant. It comes out about 8 hertz for this subject. We ran the subject twice, and they stay in phase with each other, with themselves. So it's reliable across day. And here are the 2 sessions. Again, 8 hertz. But in the group, when we've run 13 people, we're not reaching significance yet. And that's that. So we're done. And there are lots of ways we can overlap with you guys, either on the EEG or behavioral oscillations. And I'm personally on a little quest for ISIs. Anywhere we can think of an interstimulus interval, we should vary it with high temporal resolution. So and this is the team. And I feel this is very important because part of our grant is professional development. And so on the frequency tagging, our Gena Garari is going to need a postdoc this fall. So if you have funding, he's outstanding. And Kyle, who's going to need a postdoc next year. And on the oscillations, we've got Sunjin M. He's going to finish his clinical training, his internship next year. And my postdoc, Anna Ehrlichman, who I think you guys have met before. And then in Marian's lab, Dwight already has a job, and Adele and Hector will be looking for jobs in a couple of years. All right, thank you very much. And we're done. Okay.